Humanoid robots successfully perform surgery on live pigs. Could human operations be the next medical revolution? In a remarkable breakthrough that could redefine the future of healthcare, scientists have successfully used humanoid robots to perform minimally invasive surgery on live pigs for the very first time. Now let's go beyond the surface and reveal every layer of this story on our AI podcast.
Last week, down at UC San Diego, there was this living pig on an operating table, and it actually had its gallbladder successfully removed.
Right.
But the thing is, the hands holding the scalpel, the hands, passing the sutures, they weren't human.
Yeah. Not at all.
They were completely metallic, just moving with this wild mechanical precision right there over the table. And honestly, the most shocking part of this whole sci-fi scenario isn't just that robots were performing surgery.
Oh, definitely not. It's the type of robots they used.
Exactly, because these were not those, multi-million-dollar custom-built medical machines. They were literally 5-foot tall, 60-pound commercial humanoid robots, the kind you could essentially just buy off the internet.
It's wild. It completely shatters our preconceived notions of what a surgical suite of the future is actually going to look like.
Yeah.
Because, we have spent decades assuming medical robotics had to be these massive, bespoke, just prohibitively expensive machines.
Which brings us perfectly to the source material for today. We're looking at a groundbreaking study that was just recently published in the journal Nature, landing right here in July 2026.
And it is sending absolute shockwaves through the medical engineering community right now.
Oh, absolutely. So the mission of our deep dive today is to give you, the listener, the ultimate shortcut to being well-informed on this whole medical revolution.
Right, because there's a lot to cover.
Yeah, we are going to explore the underlying mechanics of what these robots actually achieved, why their specific, humanoid shape is actually the secret to their success rather than a hindrance, and how this hardware could entirely redefine global healthcare access. Okay, let's unpack this.
To really grasp the magnitude of this nature study, we need to establish the true intention behind the technology first.
Okay, lay it out for us.
Well, the cultural reflex when we hear about, robot surgeons is to immediately imagine autonomous AI just taking the scalpel from a human doctor.
Right, like Terminator and Scrubs.
Exactly. But this study is entirely about teleoperation. Humans are still very much in control. They are driving every single movement.
So the robot isn't thinking for itself during the procedure.
No, not at all. The goal isn't to replace the surgeon. It's to utilize this incredibly adaptable, off-the-shelf technology to exponentially expand the physical reach of those human surgeons.
Right, and the hardware they actually used to prove, this is what makes the study so wild to me, the research team used a Unitree G1 humanoid robot.
Affectionately nicknamed Surgie, by the way.
Right, Surgie. And we're talking about a machine that stands about 1.5 meters tall, so roughly 5 feet, and weighs in at a mere 27 kilograms.
Yeah, about 60 pounds. And that weight is a critical data point here.
Because it's so light.
Precisely.
Yeah.
You could easily just pick Surgie up, put the robot in the passenger seat of a standard car, and carry it into the building.
And what I found so compelling in the text is their whole engineering approach. The researchers didn't spend 10 years and $1 billion engineering some brand new robot from the ground up.
No, they took a totally different route.
Yeah, they took a commercially available humanoid platform and simply engineered custom adapters for it. Basically, these bespoke mechanical hands, just so the robot could securely hold standard, everyday surgical instruments.
Right.
It's kind of like taking a standard, off-the-shelf smart car and just slapping surgical tires on it, rather than trying to build a Formula One car completely from scratch.
That's a great way to look at it. What's fascinating here is the massive paradigm shift in how we approach medical device development.
Because normally everything is so proprietary, right?
Exactly. Historically, the medical sector demands bespoke engineering for literally everything, from the chassis to the microprocessors.
Yeah.
But by relying on the inherent dexterity of a commercial platform, the UC San Diego team leapfrogged years of development.
That makes a lot of sense. But they didn't just unbox it and throw it in an operating room, right?
Oh, no, of course not. Before Surgie was ever allowed to touch a living animal, they had to rigorously validate its physical resolution.
Like testing how well it moves.
Right. They put it through extensive pre-surgical benchmarking to prove it could manipulate tiny surgical instruments and handle delicate tissue without, inducing any crushing forces.
Oh, wow. Yeah, it has to translate the human operator's movements flawlessly.
Exactly. It needs the torque to crack a rib if necessary, but the absolute sensitivity to handle a millimeter-thin blood vessel.
Okay, but if I can push back on the core premise for just a second here.
Sure.
We already have highly advanced robotic surgery. Like, doctors use machines for complex operations every single day.
Right, the Da Vinci systems and similar tech.
Yeah. So why reinvent the wheel? Why are we trying to force a lightweight, walking humanoid to hold a scalpel when we already have dedicated, highly specialized surgical robots sitting in hospitals right now?
Well, to understand the engineering logic there, you really have to look at the structural realities of those existing heavyweights, like the Da Vinci surgical system. Those traditional systems are absolute marvels of modern medicine, don't get me wrong. But they are physical behemoths.
Yeah.
We're talking about machines that can weigh over 800 kilograms.
800 kilograms. Wait, so we are comparing a 60-pound commercial humanoid to a machine that weighs as much as a small car.
Yeah, pretty much.
But I assume that massive weight serves a mechanical purpose, right? I mean, you wouldn't build an 1,800-pound machine just for the fun of it.
You're right. The weight is entirely intentional. Traditional surgical robots use these massive, cantilevered arms and heavy counterweights to completely eliminate microvibrations.
Ah, to keep it steady.
Right. When a surgeon is operating, say, 2 millimeters away from a major artery, that robotic arm cannot have even a micron of a tremor.
That makes sense.
And brute mass is just the easiest way to achieve that absolute physical rigidity. But, and this is the kicker, that rigidity comes with a staggering infrastructural cost.
Oh, I bet. You can't just roll an 800-kilogram machine into a standard room.
Exactly. You would need reinforced floors.
Reinforced floors.
Yes. Reinforced floors, specialized electrical infrastructure, and dedicated operating theaters that are custom designed around the exact dimensions of that machine.
Wow.
Furthermore, you need a whole team of highly trained technicians just to manage the draping, docking, and setup sequence before the surgeon even scrubs in.
That sounds incredibly expensive.
It is. They cost hospitals millions of dollars just to purchase, which is compounded by exorbitant ongoing maintenance contracts for proprietary parts.
Okay, here's where it gets really interesting. If a traditional system requires custom infrastructure and millions of dollars, it completely boxes out smaller hospitals.
Completely.
Like a rural clinic in a developing nation, or even just a standard small-town hospital, they simply don't have the capital or the facility to support an 1,800-pound bespoke machine.
And that right there is the ultimate so what of this nature study.
Yeah.
Because Surgie is lightweight, entirely portable, and built on an affordable commercial platform, it has the potential to fundamentally democratize advanced surgery.
It just shatters the barriers.
Exactly. It shatters the physical and financial barriers of minimally invasive procedures. The vision is that a hospital that could never dream of affording a traditional system might soon be able to purchase a whole fleet of these humanoids.
And just wheel them into any standard unreinforced room.
Right, and suddenly they can offer world-class teleoperated care.
Okay, I see the financial and the logistical logic, but let's get into the actual biology and the physics of the experiment for a second.
Let's do it.
Because an 800-kilogram machine uses sheer mass to stay steady. If you swap that out for a 60-pound frame, you are relying entirely on software and motors to compensate for that lack of mass.
Yes, you are.
So can that lightweight frame actually handle the unpredictable environment, the blood, and the physical resistance of operating on living tissue?
Well, the researchers prove that it actually can. They validated the whole concept through 2 historic operations on anesthetized pigs.
Right, the pig surgeries. Walk us through those.
The first one was what they called a robot-human collaboration. So a single humanoid robot stood right alongside a human surgeon at the operating table.
Working side by side.
Exactly. Together, working in tandem, they performed a minimally invasive procedure keyhole surgery to remove the pig's gallbladder.
Which is not a simple task.
Not at all. It requires navigating through very small trocar incisions, insufflating the abdomen with gas, and manipulating internal organs with a very high degree of precision.
I mean, having a robot act as an active surgical partner alongside a human is a massive milestone on its own. But the second operation in this study is the one that really pushes the sci-fi boundary for me.
Oh, you mean the robot-robot collaboration?
Yes. 2 robots at once.
Yeah, this marked the first time in history that 2 humanoid robots jointly performed surgery on a living animal. You had 2 independent teleoperated metal machines working as a coordinated surgical team.
Just passing tools, retracting tissue.
Right, and constantly communicating spatial positioning to successfully operate on the pig without colliding into each other.
Which brings up a huge spatial dynamic question for me. If these two robots are standing right next to each other, hovering over a really small surgical field, their mechanical arms must be constantly crossing paths.
They are, yeah.
But I want to go back to the physical design of the robots themselves here, because I completely understand why teleoperation makes sense. But isn't it profoundly harder to operate a robot that mimics human arms and legs?
How do you mean?
Well, the human body is actually quite clunky. Our elbows bump into things, and our range of motion is strictly limited by our joints. So why force a robot to mimic our biology? Why not design a, hyper-efficient, specialized mechanical shape that doesn't have human limitations?
That's a really good point. From a pure mechanical engineering standpoint, a hyper-specialized shape with, say, 360-degree rotating joints might seem way more efficient.
Right.
But the researchers found the exact opposite to be true in practice.
Really?
Yeah. The human surgeons operating the consoles actually found the humanoid robots significantly more intuitive to control than traditional abstractly designed systems.
Oh, I guess because the surgeons themselves are human, so the mapping is one-to-one?
Precisely. It all comes down to kinematics, which is essentially the geometric study of motion.
Okay, kinematics.
See, a traditional surgical robot requires a surgeon to learn an entirely new control paradigm. The surgeon has to constantly translate their desired action.
What does that look like in practice?
Well, they have to subconsciously calculate how moving a master controller in one specific arc will translate to a multi-jointed, non-human mechanical arm inside the patient.
That sounds exhausting.
It is. It requires heavy cognitive load and extensive specialized training. But because Surgie's kinematics, the literal geometric constraints of its shoulders, elbows, and wrists, perfectly mirror human biology, the surgeon's brain doesn't have to translate anything.
Oh, I love that. It's like playing a video game. The humanoid shape is basically the standard controller. Our brains are already hardwired from birth to use.
That's a perfect analogy.
Right, because we intrinsically understand the spatial constraints of an elbow, whereas the giant traditional machines are like those weird, overly complex, custom flight simulator joysticks with 50 abstract buttons that take months to master.
Right, exactly. And if we connect this to the bigger picture, that intuitive one-to-one mapping actually saved the experiment from a potential disaster.
Wait, really? What happened?
Well, surgery is inherently chaotic. You are dealing with complex biological systems that do not always behave the way the textbook says they should.
Yeah, biology is messy.
Right. And during one of the procedures on the pigs, the team actually encountered unexpected minor bleeding in the surgical field.
Oh, wow. Which, if you are performing a keyhole surgery, has to be incredibly stressful. You're looking through this tiny camera feed, and suddenly the field of vision is obscured by blood.
Yes,
The
exactly.
pressure in the abdomen changes, and you have to intervene immediately.
And in a traditional setup, managing an unexpected bleed requires the surgeon to swiftly execute a complex series of instrument changes and precise movements, all while managing that cognitive load of translating their hand movements to the robotic arms.
That sounds like a nightmare in an emergency.
It's very difficult. But because the teleoperated controls of the humanoid robots were so biologically intuitive, the surgeons didn't panic or fumble with the interface.
They just reacted.
They simply reacted as if their own physical hands were inside the patient. They clamped the bleed, managed the tissue, and stabilized the pig with zero major complications.
That is incredible.
The research team explicitly noted how seamlessly the humanoid system allowed the surgeons to handle a real-time biological crisis.
So the intuitive nature of the hardware essentially eliminated the interface barrier during an emergency.
Exactly.
The pig survived, the bleeding was controlled, and the hardware proved it could definitely step into the operating room. But let's pivot to the reality check for a minute.
Good idea.
Because I don't want anyone listening to think they're going to schedule a surgery next week and see two humanoids standing over their bed.
No, we're not there quite yet.
Right. The study outlined 3 major technical limitations that the engineering teams are still grappling with. And the first one listed is recalibration.
Yes.
If these lightweight robots are relying on software rather than 800 kilograms of mass, I imagine the software occasionally gets confused about where the robot's arms actually are in physical space.
You are touching on the absolute core engineering bottleneck of lightweight robotics right there. It is known as sensor drift.
Sensor drift.
Right. As the robot operates, its joints physically heat up. Thermal expansion subtly changes the mechanics.
Oh, the metal actually expands.
Just a tiny bit, yes. Furthermore, As the robotic arms push against the physical resistance of muscle and fascia, the microsensors and gene encoders experience mechanical stress.
So they get bumped out of alignment.
Exactly. Over time, the physical arm might be a millimeter or two off from where the software's spatial map thinks it is.
And a millimeter discrepancy in surgery is the difference between nicking an artery and a successful operation.
It's a huge deal.
So what do? Do they have to physically pause the procedure, just halt all movement, and recalibrate the software to reestablish the absolute 0 point of the robot's limbs?
Yes, that is exactly what they have to do. They had to frequently interrupt the operations on the pigs just to reset that spatial awareness.
Wow.
And obviously, in a critical human surgery, you cannot simply pause the operation for 5 minutes while the patient is under anesthesia to reboot the hardware.
No, definitely not. Which naturally leads into the second major limitation the study highlighted, which is time.
Right. Time is always a factor.
If you are constantly stopping to recalibrate the sensors, the procedure is going to take significantly longer.
And it did. The pig surgeries took considerably more time than they would have using traditional surgical methods.
Ah, okay.
Though we do need to view that limitation through a historical lens, to be fair. Well, if you look at the early iterations of traditional robotic surgeries a couple of decades ago, those initial procedures took hours to complete as surgeons learned the systems.
Oh, that's true.
Today, those exact same operations are routinely knocked out in under 30 minutes.
Just because the tech got better.
Tech improved and surgeons got faster. As the encoders become more resilient and the software gets better at predicting thermal drift, the speed of these humanoid procedures will naturally increase.
Okay, so sensor drift and procedure time are massive hurdles, but solvable ones. But the third limitation they outline is the one that seems the most dangerous to me, and that's control latency.
Latency is the ultimate adversary of teleoperation.
Right.
It is the microsecond delay between the moment the human surgeon moves their hand at the control console and the moment the robot's metal hand actually mimics that movement inside the patient's body.
See, if I'm on a video call and the audio lags, it's annoying. But if a surgeon is hovering a scalpel over a vital organ, and the visual feed and the physical response are separated by even a fraction of a second, that is a catastrophic safety risk.
It really is.
Because tissue moves, a patient breathes, the heart beats. If the robot is executing a command based on where the tissue was 200 milliseconds ago, it is cutting in the wrong place.
And this raises an important question about the immutable laws of physics.
Yeah.
Because we are dealing with network packet drops, fiber optic routing delays, and the literal speed of light. Even with highly optimized networks, asymmetric routing can cause the video feed to desync from the haptic feedback.
So what they see isn't exactly what they feel.
Exactly. And if the surgeon cannot trust the real-time accuracy of their visual field, they simply cannot operate safely.
Okay, so if they aren't ready to be the primary surgeons on human beings just yet due to sensor drift and latency, it really begs the question of how this technology integrates into the hospital ecosystem in the short term.
Right. What do we do with them now?
Exactly. We have these highly capable 60-pound robots that work incredibly well, but they require a perfectly optimized zero-latency environment to wield a scalpel safely.
Well, the researchers actually propose a highly pragmatic short-term integration. Before these humanoids are ever tasked with cutting human tissue, they will likely be deployed as highly intelligent surgical assistants.
Oh, okay. Just helping out.
Think about the chaotic environment of an active operating room. A humanoid robot doesn't need zero-latency perfection just to walk across the room.
That's true.
It can be tasked with fetching sterile instruments, adjusting the heavy overhead surgical lights, managing the sterilization of equipment, or even running critical blood supplies down the hall.
So you basically act as the ultimate OR support staff, handling all the logistical overhead so the human doctors and nurses can remain entirely focused on the patient.
Precisely. And the global medical infrastructure desperately needs that logistical support right now.
We really do.
We are currently facing a massive, compounding shortage of trained surgical staff worldwide. Millions of patients are experiencing delayed, life-threatening wait times, not because we lack the medical knowledge to treat them, but simply because there aren't enough hands in the hospitals.
So a robot assistant could free up those human hands.
Exactly. Deploying a fleet of humanoid assistants could drastically reduce the physical and cognitive workload on our human medical staff, allowing the existing workforce to treat more patients with a much higher degree of safety.
That makes a ton of sense for the short term. But the long-term vision, assuming we continue to optimize network architecture and minimize that latency gap, is what truly redefines the whole field.
It really does. The senior author of the Nature study, Professor Michael Yip from UC San Diego, actually laid out a trajectory that pushes well beyond the standard hospital setting.
Where is he looking to take this?
Well, once latency is brought down to a negligible threshold, an expert surgeon sitting at a console in New York could take real-time control of a Surgie robot located in a rural, underfunded clinic in sub-Saharan Africa.
Wow.
They could operate on a wounded soldier in an active military conflict zone without ever putting specialized medical teams in the line of fire.
Or like disaster relief.
Exactly. They could provide emergency trauma surgery in the middle of a hurricane disaster zone where traditional transport is impossible. Professor Yip even projected this architecture out to space exploration.
Space exploration, like operating on astronauts.
Yes. Teleoperating these humanoids in lunar habitats or future Martian colonies where it is physically impossible to keep a diverse staff of surgical specialists on standby.
That is just mind-blowing. Okay, so what does this all mean for you, the listener, navigating this rapidly changing medical landscape?
It's a lot to process.
It is. If we distill the profound engineering achievements of this nature study, the narrative is really clear. Humanoid robots are not marching into your local hospital to replace the human surgeon.
No, they aren't.
They are arriving to serve as incredibly precise, highly portable, 60-pound extensions of that surgeon. They represent a fundamental shift in hardware design, moving away from those 1,800-pound behemoths toward agile commercial platforms.
It's a total game changer.
It is. They are the tools that will finally allow the absolute best life-saving medical care to break out of the expensive, reinforced operating theaters of the West and reach the most remote, underfunded, and dangerous corners of the globe.
It is, at its core, a deeply democratizing force in global medicine.
Absolutely.
But, I want to leave you with one final thought to mull over, building on the mechanics of teleoperation we've been discussing today.
Okay, let's hear it.
Right now, the entire paradigm relies on a human directly controlling the robot in real time. But every single time an expert surgeon operates that console, the computer system is meticulously logging the data.
Recording everything.
Yes. It is recording the exact spatial movements, the precise pressure applied to the tissue, the specific angle of every single cut.
Wait, so it is essentially building a digital archive of physical expertise.
Exactly. So what happens when that system gathers enough operational data from the top specialists in the world?
Oh, wow.
Could we eventually transition from live teleoperation to recorded execution? Imagine a future where a robot in your local small-town clinic doesn't just allow a remote doctor to dial in live.
It just knows what to do.
Imagine if it actually downloads the precise, historical, physical movements of the world's absolute best cardiac surgeon for your specific procedure.
That's incredible.
The humanoid robot simply replays the maestro's physical performance, perfectly adjusted to your biometric scans. It would turn every single local clinic on Earth into a masterclass in surgery, giving you the best physical hands in human history whenever and wherever you need them.
The actual physical muscle memory of the world's greatest surgeons just downloaded into a 60-pound robotic frame at your local clinic. That is wild. Well, thank you for joining us on this deep dive.
It's been great.
Stay curious, keep questioning the mechanics of the world around you, and don't let the rapid pace of the future overwhelm you, because we will always be right here to help you.
Okay, one question for you. Would you feel comfortable allowing a humanoid robot to perform a life-saving surgery on you if experienced surgeons were remotely controlling it? Or would you still prefer a traditional human surgeon? Explain your choice. Thanks.